All right, kids. So now today we are the main topic that we're going to do. This is the last one, and that's called astrophysics. For astrophysics, the first thing you guys need to remember is luminosity. Now, astrophysics is kind of a topic that you will find a lot of pieces like here and there. And at the end of this chapter, you realize that we're going to connect each and everything together. So let's have a look at it now. So luminosity is defined as the total power output of radiation emitted by a star. It's basically power output, so it means it's equal to the radiant energy, the energy that it is radiating out per unit time as well. You can also say that to it. Obviously, because it's output power, so that means the SI units of luminosity would be watts. It's also understandable that because it is power, it is a scalar quantity, and the symbol that we use for luminosity is capital L. Now remember, sometimes they use this symbol. Note, luminosity of sun is written as this L and a circle and a dot. So that means it's sun, okay? Equals to 3.83 times 10 raised to power 26 watt. You don't need to remember this value, it's just the way it is written. So I wanted to show you that. All right, kids. Now, write it down, please. Now, then comes something called radiant flux. Now, this is so important. So, radiant flux basically means the amount of intensity observed normally. Normally means at 90 degrees, all right, through a surface per unit area of radiation measured on Earth. The symbol for radiant flux is F, and the SI units, because it is power transmitted per unit, area. So it's watt per meter square. Okay, now, so what happens next is that suppose there is a star. I hope the star is drawn like that. And obviously, the star, which sort of looks like this, is twinkling, right? Which means it's radiating energy from all sides, like that. Now, back on Earth, which is a small place, the star, from one point, it's sending energy to all directions, like that. Uh-oh, that's bad. Oh my god. Doesn't come from the same point. So but it thinks I want to snap there. Wait. Let me draw it from here. Crazy software sometimes. Okay. Now, what you guys need to remember is that the flux, radiant flux, is measured by whatever the luminosity of that object is divided by the surface area. 4 pi d square, right? Like that. Well, this is 4 pi d square is the surface area of sphere, right? So here, just remember this formula, like that. Now remember, right here, let me write it down. Luminosity is the total radiation that leaves the star. Then the radiant flux intensity is the amount of radiation measured on Earth. Like that. Now, as you can see, it starts from a single point, but the time it reaches us, it has basically spread too much. As you guys can see, that becomes a whole, big circle like that. So, by the time radiation reach us, it has spread out by a huge amount. Therefore, only a fraction of it is received on Earth, right? So it only is this much that the circle of Earth is like that, right? So surface area is like that. Otherwise, everything is like going to spread. Okay, please write this down and let me know if you have a question here. Okay. Now, obviously, this whole thing, let me see how much space I got. I don't have it. I got to go to the next page. All right, kids, should I go to the next page, please? Now, in this one, you guys need to remember that this law follows the inverse square law because it has a d square at the bottom, right? Now, suppose this is the sun or any star, for that matter of fact. So, this star, every time it radiates energy, oh, wait, like that. Wait a second, let me make three sizes of it. Okay. So this star would then, this light from a single point from the core is basically moving like this, right? Oh, I should have known better. Chalo Prabhat. I have to use the ruler actually. Do that. Too tough to redo the windows actually. Chalo. So bad. That is not fair. Like that. Let me remove these windows. It's not required anymore. Like that. And like this. Okay. Now I'll draw the windows. Wait. So every time you go a distance higher than this, the area becomes more and more like that. Okay. Now, what I want to show you from this drawing is that actually, if you have, suppose at a certain distance, hello, वालेकुम सलाम, जी जी ठीक है एक सेकंड. All right, kids. So at suppose distance r, we have, or you could say distance d, we have this flux. So at like 2 times the d, now at 2 times the d, the flux is going to be a quarter now because basically the area keeps on getting bigger and bigger, right? And similarly, if I go to this end, so So at this end, which is 3D, then I will have 1 upon 9 flux. So it is an inverse square law. And it follows through all this because if you know that the surface area of star would be 2 pi r square. Now, so basically, we can say wherever it's going, it keeps on spreading. So radiant flux intensity F is equal to or proportional to 1 upon d square, like that. You got to remember this, all right? Now, for this formula to work, which is F equals to luminosity over 4 pi d square, luminosity of a star is constant and 4 pi is also a constant. Just remember there's some assumptions to be made. The assumptions are as such. Number one, the power of star radiates uniformly through space. This is the first assumption. And the other is that no radiation is absorbed between star and Earth. These are the two assumptions we make for this formula to work. Now, from the same formula, we have basically made a couple of other, uh, you say, discoveries. Number one, luminosity, which is the power of a star, is a constant, which means each star would have the same, or same type of stars would have the same. The radiation flux, or radiant flux, we can write it. Radiation flux follows an inverse square law. Number three, the greater the radiant flux, intensity measured on Earth, the closer the star is to the Earth. Because as you know, as you can see, the further away you go from the star, its flux intensity is gonna get reduced by a function of square. So you guys need to remember that as well. All right. Let me know if you have a question here. Right, kids. Now, let's look at a question and see how to use this formula. So, in a question, it states that the distance of a particular star is found to be 3.8 into 10 raised to 18 meters. The radiant flux received is 2.6 into 10 raised to minus 9 watts per meter square. Now, considering the star radiates uniformly through space, calculate its luminosity. That's the question. Can you guys please try this? Take 2 minutes. Try this, so then we'll go forward.
How long is this chapter anyway, sir?
This chapter,
Yes.
I think it's gonna take this week and one class from the other week.
Okay.
Yeah,
Because I was wondering if we could cut class short today.
cannot do that. It's a kind of a full unit. So,
All right.
all right, quickly, please answer this. Okay, quickly, please answers. It's easy.
I'm getting 4.72 times 10 to the power 29.
That's correct. So it's you just need to use this. This is 2.6 into 10 raised to minus 9. This is the luminosity you want to find, 4 pi, and 3.8 into 10 raised to power 18. How where am I writing this? 18 whole square. So you should be getting 4.72 into 10 raised to power 29 watts, like that. Very good. Now, there's something very important, and we tend to use this to find distances of different stars, and that is known as standard candles. What is a standard candle? Explain that to you in a bit. Okay. So, standard candle is defined as an astronomical object which has a known luminosity due to a characteristic which is basically a quality, okay? Quality possessed by that class of objects. So I'll explain that in a bit, what it means. Why do we call these kind of things standard candles? But first of all, but first we're going to learn about some of the examples of standard candles. So the first one is the Cepheid variable stars. Now, a Cepheid variable star is a type of pulsating means twinkling star, that increases and decreases in brightness over a set time period. So the characteristic we're looking for is the time period that it twinkles to. All right. The variation, the variation has a well-defined relationship to the luminosity. Then, so we can get to know the luminosity and compare it with other stars like that. The other standard candle we take is called type 1A supernova. We're going to learn supernovas more. So you can, in plural form, you can write supernovae. So a supernova explosion involving a white dwarf. This is basically the end stage of a normal star. The luminosity at the time of explosion is always the same. So that's why for any of these type 1A supernova, we take it as you know standard candle.
You mean if two different white dwarf stars goes supernova, their luminosity will be the same?
Yeah, for white dwarf is basically small, less massive stars. For less massive type stars, we take one type 1A as supernova, standard candle, right? That's fine. Now, all these things that I say, these are discoveries. So, from so many years, we have discovered these, and these are facts. We cannot change those. Okay. Now, the first task we have is obviously when you find a standard candle, we know there is a standard candle. We can, try to see what would it give us. Basically, standard candles are used to help us find large astronomical distances of distant stars, right? So that's why they're good in that. So the thing is that measuring astronomical distances is an extremely difficult task. Like we just can't predict, right? It's so large. A direct distance measurement is only possible if the object is close to the earth. Now, for distant objects, we use indirect methods like standard candles as a distance indicator because we can compare, right, to then the nearby stars. Now, how do you compare that? That if, suppose, from radiant flux, right, if luminosity is known of a source, We'll learn further how we can find that. Then the distance can be estimated based on how bright it appears on Earth. All right, let me just explain this in a bit. Let's suppose there is a table that you're sitting on. Sorry, beside that table, you're sitting there on a chair, and on that table, you have kept different candles. Let me just draw that so you guys have an idea what I'm talking about. So there are numerous candles you put, right, of same type at different distances, right? So they're all same type candles, and each candle is lit. And you're just sitting right here. Okay, so there's a person sitting here. So this person is viewing these candles from this side. His distance from this candle he knows is d, right? So which of these candles A, B, C, D, and E is going to be would look the brightest to him? What do you guys?
A.
A. The reason why it is brightest because it is closest to him. Do you guys understand that? The dimmest candle would be which one?
E.
E, because it is the farthest away. So if he knows the distance of A, and then he knows that okay, the brightness of E is this much smaller, the flux that he's been receiving this much smaller, then he can find the distance to them because he has now fixed A as the standard candle. Is it clear? So it's as simple as this, right? So just estimation of how far it would be, but these are pretty accurate, it's not that bad. So we can say that astronomers measure the radiant flux intensity of electromagnetic radiation arriving at Earth. All right. Now, since the luminosity is known as the object is a standard candle, the distance can be calculated using the inverse square law, which is F equals to L over 4 pi d squared. This is why we have done so much. Is it clear, everyone? The last thing we're going to do is then A question that they may ask you is, what is a cosmic distance ladder? All right. So they will ask you this word, this sentence actually. So what you do, you should remember that each standard candle method can measure distances within a certain range. Obviously, you have to see them. Now, collecting data and measurements from each method allows astronomers to build a larger picture. Oh my god. Larger picture of the scale of universe. So every time we make a discovery, we add this element to the picture, and this is known as the cosmic distance ladder. Is it clear, kids?